Yep.
All right. Thank you for letting me know. Okay. So just to repeat that, we're thinking about the angle theta as a kind of angular position. So it tells us where an object is at, not along the x-axis, but as it rotates, where it's at in rotational position. So we're going to think of it as a kind of position. And analogously to velocity, angular velocity, which is this, lowercase omega, looks like a curly W, but we pronounce it omega, tells us how fast the object is spinning, and the sign gives us which direction. So for example, if we define which way we mean to be the increasing theta direction, so this is the positive theta direction, this is the negative theta direction, then if it's spinning so that theta is increasing as time goes on, we call that a positive omega. And if it's spinning in the opposite direction, so theta is decreasing as time goes on, that's a negative omega. And similarly, angular acceleration tells us the rate and the direction in which omega is changing. And just like regular linear acceleration, it's somewhat confusing about the sign. It's easy if something has a positive omega and it has a positive alpha, that means it's speeding up. If it has a negative omega and a negative alpha, that means it's speeding up in the negative direction. But if it has a negative omega and a positive alpha, that means it's spinning in the negative theta direction, but slowing down. So it's trending towards the positive direction. Okay, so that's the position, velocity, and acceleration for these rotational variables. And angular acceleration is the Greek lowercase alpha. Similarly, there are relationships between, if you watch a point on an object that's rotating around a fixed axis, of course it's going in a circle as time goes on. And we might ask about the relationship between how far it moves and the angle that it's rotated with. And that depends on how far it is away from the rotation axis. So this tells me, if you know what angle it rotated through, this is how far it moved in distance along that arc length. If this is how fast the object is rotating in radians per second, then this is going to be how fast it's moving through space in meters per second. And if alpha is the angular acceleration, then that tells me something about the rate at which it's accelerating along the direction tangent to the circle that it's moving on at that instant. And the radial acceleration, or sometimes we call it the centripetal acceleration, is the component of the acceleration towards the center. As long as it's rotating at all, as long as omega is not zero, it has some centripetal acceleration. This is just the same old v squared over r, but we rewrote it in terms of omega rather than v, because we wanted it in terms of rotational quantities. So these relate rotational to linear quantities that we talked about before. And for all of these, they started with this one, which had to be true in radians, and we use that all the way down. So theta, omega, and alpha have to be in radians units. That means something like omega in radians per second, alpha in radians per second squared, theta in radians. Otherwise, you'd need an extra factor put into these equations. Okay, continuing with our analogies. There's a whole lot of analogies between linear motion and rotational motion. Just like we had our linear kinematics equation that all flowed from the idea that AX is constant. It's not changing with time for a period of time. Here, we can start with the same assumption that alpha is constant for a period of time, t. And this tells us how theta varies as a function of t, omega varies as a function of t, and omega as a function of theta. And notice they're exactly the same as these equations, but we just replace each variable with its rotational analogy variable. So x becomes theta, vx becomes omega, ax becomes alpha. And they're the same equation. So I want to do a worksheet to practice with, just thinking about how to translate between these. For those of you on Zoom, this is, I believe, a worksheet that was posted under Monday's date on the website. We just barely missed getting to it. So here is, for some reason, I don't know why this figures so strongly in physics textbooks, but there's always problems about grinding wheels, as if people are using, I guess if you're a mechanical engineer or something like that, or someone who uses tools a lot, you do use grinding wheels. But if you've ever turned on a massive wheel, it does take a while to get up to speed. And when you turn it off, it spins for a while and slowly slows down its rotational rate, right? If you've ever sharpened a tool on, a gritty wheel, that's called a grinding wheel. You can use it to sharpen your metal tools. And you turn it off and it might take 10 seconds to come to rest. So that's the kind of thing we're talking about here. So here's a grinding wheel that is initially spinning. From your point of view, it's going counterclockwise at 1,000 revolutions per minute. And we'll say at time we define to be 0, the power is switched off, and it takes 12 seconds for it to spin down to rest. And we're going to assume that it need not be the case that angular acceleration is constant during that period, but we're going to assume that it's constant, much the same way we assumed earlier that when a car puts on its brakes, we might say, pretend that the acceleration is constant as it comes to rest. So in this case, angular acceleration is constant. And we're supposed to calculate a bunch of things here. Maybe let's do A and B together just to get the feel for it while those are up there. Okay, so I want to have this in the video, so let's show the board. We won't be able to see our kinematics equations, but it will give us a chance to challenge ourselves to remember the kinematics equations and translate into angular form. The first question is, given all this information, what is the angular velocity at time t equals 0 in radians per second? It was given in RPMs, revolutions per minute. So for A, how do I, we would still call it an omega. It's just in different units, right? We're told the angular velocity in this case is initial angular velocity at t equals 0. In terms of our kinematics equation, I usually put a 0 on that to indicate time t equals 0. Is 1,000, I'm going to write out RPMs, revolutions per minute. How do I change that to radians per second? What would I do? Austin? Yeah, I've just got to convert each one of those one at a time, right? So you're saying 2 pi radians, we're just changing units, is the same thing as 1 revolution. We learned that last time. So that's one of those things you're going to have to kind of just remember. Also, pi radians is 180 degrees if you're going between radians and degrees. That's good because we didn't want revolutions, we wanted radians. And the minutes, of course, is easy. 1 minute is the same thing as 60 seconds. And so when I cancel my minutes, I have radians per second, the number being 104.7. Radians per second. So the SI units for omega are radians per second. SI units for alpha are radians per second squared. Okay, why do we care? Well, we're going to use this in kinematics. We could even do this in B. My solution wasn't written in terms of kinematics, but we could do it in terms of kinematics. What's the wheel's angular acceleration? In B, in other words, I want to find alpha. We're told alpha, we're supposed to assume is constant throughout the whole slowing down process. Anybody have an idea how I might apply a kinematics equation to solve for alpha? Yeah, the second, I know which one is the second one because we just looked at them and I think they're in the same order I even did way back when. It says this, omega final is equal to omega initial plus alpha times t, where t again represents the time that elapses between the initial and the final condition. Okay, so we now know omega initial in radians per second. Do we know anything about omega final? Our goal is to get alpha. The t between initial, I'm taking final to be when it comes to rest. T is 12 seconds, I believe, in this problem, right? What do we know about omega final? It's 0, right? It's not rotating anymore after 12 seconds. So the omega that corresponds to putting 12 in here, we have to add to 104.7. And again, I'm sort of suppressing units as long as they're all SI units, and then I don't have to think so much about it. I can solve for alpha. Minus 104.7 over 12, or minus 8.73 radians per second squared. Right? I solved for alpha. Everything else was in SI units, so alpha has to have SI units. Now, I guess I need to read this again and make sure that that minus sign is justified. Yes, so here it says, call the direction it's spinning positive angular velocity. So it's spinning in the positive direction, whichever direction it's spinning, we're going to call that direction of increasing angle, right? That's the positive spinning direction. Positive angular velocity. If it's slowing down, I'm expecting a negative angular acceleration, right? If I had positive angular velocity and positive angular acceleration, it would be speeding up as time went on. So that makes sense in terms of the convention that's being applied there. So there's B. All right, why don't you work on C, D, and E? More kinematics there, just trying to answer different questions. I'm going to give you maybe 5 minutes to chew on those, and then we'll come back together and finish them. Okay, let's work on C, D, and E together. Wheel's angular velocity after 3.7 seconds. So it takes 12 seconds to come to rest. It still should have some positive non-zero value of angular velocity because it's on its way to rest. Same equation will get us there as before, right? Omega final is equal to omega initial plus alpha times t. We now know what alpha is. It's constant all the way through. And now I'm just going to plug in t equals 3.7 to find omega final. I want to find omega that corresponds to t equals 3.7 seconds. My alpha I already know is minus 8.73 in SI units. And omega 0 was 104.7. So this subtracts a little bit off of it, and we're left with 72.4. With everything in SI units, I can then confidently put radians per second on there, the SI unit. Okay, any questions on that? D, how many revolutions does the wheel turn through from time t equals 0 until stopping? So it starts out going really fast. It's turning through so many revolutions, and there's a definite number of revolutions by the time it comes to rest. How many complete turns does it go through on the way to rest? Who has an idea for how we might approach that one? Yeah, Abby.
I did the kinematics where it's like theta equals theta initial.
Right. Yeah, so I think you're thinking, let's call theta 0, the theta it's at time t equals 0. By definition, that will be theta equals 0. Or, you can always subtract it off and you can say, look, this represents how far it's moved since time t equals 0. I don't have to call that 0, but this is how far it's rotated. Okay, and that's equal to omega 0 t 104.7 times t, and we want to know theta minus theta 0 for those full 12 seconds. That's why I'm putting in t equals 12. Plus 1/2 alpha is minus 8.73 times t squared. And I calculate that number, that's the angular displacement. I get 627.8. What units should I put on that? Radians, the SI unit for angle or angle displacement. Now that's not what was asked for. That's how many radians it rotates through. We want how many revolutions it rotates through. So can't I just now take that number and do a unit change on it? If I want revolutions, I could say 1 revolution is the same thing as 2 pi radians. And then I have to divide that number by 2 pi. So I end up with 99.9 revolutions. Okay, somewhat interesting that it rotates almost exactly 100 times around. E, what is the wheel's angular velocity after it has moved through 60 revolutions after time t equals 0? So here we're not given the time, we're saying it does 99 revolutions, but after only 60 revolutions, how fast is it spinning then? So in more common language, what we want to, how could we approach that one? It's a kinematics kind of problem, but what kinematics equation? Edward Lee? Yeah, the famous third kinematics equation. Now, nobody else will know what you're talking about if you say the third one, but for us, it's okay. The third one in angular quantities is omega final squared equals omega initial squared plus 2 alpha delta theta. And the delta theta that we're interested in is 60 revolutions probably, to be safe, I should convert that to radians, and then I can put everything in radians, and I'll know what units to put on the final answer. 60 revolutions is the same thing as, well, 2 pi radians is the same thing as 1 revolution. So just changing units there. You know, I don't have my calculator here, and I don't have it on my sheet here, but 60 times 6 is about 360, close to it. Somebody can tell me what the exact number is? 0.99. So we'll call it 377 radians. We're interested in how fast it's going, or its angular velocity at that final. So we can say omega final is equal to the square root of omega initial squared, 104.7 squared, plus 2 times minus 8.73 times 377. All of that under the square root. I see something in my solution that looks like a mistake, so you guys can tell me what the real one should be. Yeah. 66.18, and the units are going to be SI units because we put all SI units in everywhere else. Good. Any questions on that? Just the kinds of problems we would have done very generically in one-dimensional kinematics. We're just getting used to using them in angular sense. All right. Okay, and this is the solutions just shown up there. Here's another interesting thing. If we have, we haven't talked much about wheels rolling on the ground, but any round object, a wheel, a ball, a can, oftentimes rolls without slipping. Now, rolling with slipping means that's like if you're in your car, you're peeling out, right? That's rolling with slipping. The normal way we use wheels is they do roll without slipping. That means they're not actually rubbing in a kinetic friction sense against the surface they're rolling on, but rather they're coming down and momentarily just touching, but not slipping while they're touching. They're just coming and touching at rest without moving relative to the surface, okay? That's called rolling without slipping. So here's a wheel I'm imagining rolling along to the right. Here it is, partway to the right. Here it's gone through exactly 1 revolution. So this red mark on here has rotated all the way around and gotten it over there. The question I want to address is, well, the center of this is moving at a certain speed as I watch it go by. It may or may not be an axle on this thing, but I'm just going to call it V axle, or you could call it V center of the wheel or something like that. Furthermore, if you were riding around on this thing, so you're moving along with the axle, it would be spinning around the axle at a certain rate. And the question we want to address is, how is the speed of the axle as you watch it go by related to the speed at which it's rotating around the axle, which it would be a pure rotation if you were riding along with it. Because oftentimes we're going to be interested in things that roll without slipping. Clearly, the faster one is, the faster the other one is. In other words, if this thing rolls twice as fast, it seems like the omega is going to be twice as big if the axle is moving twice as fast through space, right? It's going to go through the same number of revolutions in half the time in that case. So what's the relationship? Here's one way to disentangle it. I can look at this image where it's rotated through exactly 1 revolution. So I've painted a red strip on it. That red strip happens to be down here. It's down again, so it's gone through exactly 1 revolution there. And the key thing is the distance it's moved through. If the radius of the wheel is r, the distance it's moved through is 2 pi r. You can think of wrapping a piece of paper around the circumference of the wheel. and letting that paper lay out on the ground as it rolls over here. And all the paper would have unwound from it by the time it goes through one revolution. That paper has length 2 pi r because it exactly fits around the circumference, okay? So in terms of that, the speed of the axle is the distance it moves, which we just discovered we can write as 2 pi r, divided by the corresponding amount of time, which is the amount of time it takes to go that distance. We don't need to know that. You'll see why in a second. Now, I'm going to re-express this 2 pi. You know, we thought of it as just part of the circumference formula, but now I'm going to think, well, that 2 pi is also the angle it rotated through. It rotated through a complete revolution. That's 2 pi radians. So I'm going to reinterpret the 2 pi as just delta theta. And then delta theta over delta t is omega, right? It's the average omega, but we're imagining here that this thing's moving along at constant speed. And therefore, the relationship between the speed of the axle and the rate at which it's rotating about the axle is v axle equals r omega, which, you know, a little bit confusingly, we already had an equation that said v equals r omega, which meant something a little bit different. That meant if we had an object, you know, it doesn't have to necessarily be a circle, and we were looking at a point on there. So here is my axis of rotation, and I would like to know what is this. So this point is moving around in a circle as this thing rotates. How does its speed here relate to this rate of rotation omega? And we found out, well, it depends on the r you're at, right? Speed v equals r omega. This has although it looks almost the same, it has a completely different interpretation. This is saying that here, the axis of rotation in one point of view isn't fixed, it's moving through space. But we can also imagine riding along with it, and then it would be in pure rotation. If I just look down and I'm on my bike and it's rolling without slipping, I'd say my wheel is just rotating about a fixed point relative to me. So that allows us to solve questions about things, you know, like bikes and cars. So here, problem number 2, which we're going to work on now, and I'm not going to do this one together, so you can just start working on it. Here's a car. It's got 30 centimeter radius tires. That sounds kind of small to me. I just make up these numbers, you know, 30 centimeters, you know, that's about this big. That would mean the car, this is like, I don't know, probably not a typical race car. Who knows, maybe Indy cars are like that. Begins slowing from 20 meters per second to 0 meters per second. So it hits the brakes and it takes 8 seconds while traveling in the plus x direction. So as it's moving in the plus x direction and slowing down, the wheels are rotating in the counterclockwise direction. Everybody knows clockwise means the direction a clock turns, right? So the wheels in this case, as the car is moving to the left, will be rotating in the counterclockwise direction. And we're just going to call that the positive rotational direction. So those would be positive omegas, just for definiteness. What's the angular velocity of one of the wheels at time t equals 0? What's the total number of revolutions each wheel goes through before stopping? And is there a third question on here? No, that's it. So take a couple of minutes, see if you can answer those. You might need some kinematics, but you might also need v axle equals r times omega. That's true at any instant in time, even if v axle is changing. That's just going to tell us that omega changes, and it's true at every instant in time. Okay, some are finishing up with B, some are still on A, but let's go through it together. And I'm just going to do it up here on the screen. What's the angular velocity of one of the wheels at time t equals 0? This relates directly to this relationship we just derived. V axle equals R omega. We know at time t equals 0 how fast the axle of the car is moving through space on the road. At time t equals 0, it's moving at 20 meters per second. So that's our V axle. And so we're just going to set that equal to R times omega. And here we're talking about a round object. So R is the radius of the wheel or the ball or whatever it is that's rolling. It's got to be a round object. And we can solve for omega. Now, in this case, you know, I'm not worrying too much about the signs. I'm saying, you know, I know the speed of the axle, and that's going to give me the absolute value of omega if I don't think about the signs too much. Since the way I've lined things up here, when V is positive, omega is actually positive too. That need not be the case. But in this case, it just tells me about how fast it's spinning. So 20 over 0.3 is 66.67 radians per second. That's the initial angular velocity of one of the wheels. And then we're going to use that to find the total number of revolutions each wheel goes through before stopping. What are we told here? We're told the time. So it looks like we want theta versus t, right? Theta tells us about revolutions, and we're given a t it takes to stop. So let's now apply that equation and figure out what theta minus theta 0 is. To use it, I'm going to need to figure out what alpha is. You know, I'm writing alpha as delta omega over delta t. That's really the average alpha, but if alpha is constant, and we're told to assume alpha is constant here, the average alpha is equal to the instantaneous alpha. But that's the same thing we got before by saying omega final is equal to omega initial plus alpha times t. If I solve for alpha, don't I get omega minus omega 0 over t is alpha? That's really the same equation, right? How much omega changed by divided by the amount of time that elapsed between those two omegas. So same, you could have gotten this from a kinematics equation right here. So I got my alpha, I've got my t that I want to plug in, so I'm just going to see what theta minus theta 0 is. Again, t is 8 seconds, and plugging that all in, I get 266.69 radians. Again, it's tempting to box it, but we're asked for revolution, so I got to do a little conversion. 1 revolution is the same as 2 pi radians, so that's a smaller number of revolutions, 42.4. Questions on that? All right. please stop me if something doesn't make sense. This is supposed to be the kind of straightforward part. Yeah, it's a little bit confusing and something I didn't really mention too much. Let's go way back. Oh, this isn't good for fast forwarding back. Let's go way back here to the beginning where we talked about the definitions of radians. All right. The very definition of a radian was this distance S over this distance R, right? That defines an angle. And now if you think right here, what are the units of radians? Well, S would be measured in meters, right? It's a distance of that arc length. R is also measured in medians. So you think in meters. So theta in radians really doesn't have any units at all. And sometimes people sort of throw in irradians if you want to remind people that there's an angle there, but a lot of times people just leave them out. And they would write radians as seconds as just radians per second as 1 over seconds. So radians really have no units whatsoever. But we could still convert them to other ways of measuring angles like their irregular unit. So to answer your question, to go back to that solution as I fast forward here. Let's see, somewhere here. We have meters per second divided by meters gives 1 over seconds, but that's the same as radians per second because radians is the same as no units whatsoever. And it's a little bit confusing, but a radian is defined as a ratio of distances, and therefore there are really no units associated with radians. It's a dimensionless quantity, sometimes people say, because it's a ratio of 2 things of the same type. So you'll see sometimes people willy-nilly put in irradians or take out irradians. I like to put the radians in because it's sort of easier to understand. If you write this as 1 over seconds, unless you're used to seeing that, you might think, oh, wait a minute, why is that an angular velocity? Well, it is because the radians can be put in or taken out at any time. All right, so we're going to go on and talk about torque now for the last 15 minutes, which is just another kind of topic. We're on our way to kind of F net equals ma for rotational motion. Again, we're going to build up a lot of analogies here. So this is a voting question. The answers are A, B, C, D, E, or F. You can, if you don't have your voting card, you can hold up fingers here. Let's imagine there's some rusted nut here that really doesn't want to turn. You got this really long wrench, and you can apply the same force in any one of the these 2 locations in 3 different directions. And just, I want you to use your intuition. Which one do you think would be the most likely to get that nut to turn, given that you're pushing with the same force in all these different directions and in the 2 locations? And if you don't know, you can just think, well, if I were going to pull on it and I didn't think about it, which way would I grab and pull? Where would I grab it and which way would I pull? You have a lot of intuition about this just from dealing with ordinary objects. Okay, let's see a vote if you got it. Hold up your fingers. I've got a... You know, I'm seeing a variety of answers. Probably E is slightly more numerous than the other ones. It's certainly not a majority, but there are lots of other ones here. And E actually is going to be the most effective. Let me see if I can do this by, well, let's see, I guess I got to aim the camera over here at the door. But, you know, let's think about trying to open or close a door. Now, a door is usually pretty well lubricated, but still it's kind of hard to get it moving. And so let's imagine I want to open this door over here. Or maybe I want to close it. I've got it opened and I want to close it. And I have a choice of pushing here with a force we're pushing in here really close to the axis of rotation. Now, you probably have the intuition that if you're going to push in here an inch away from the pivot axis, you're going to have to push really hard to get it going, right? Whereas I can push with a modest force and really get it going pretty easily over there. So the same force is much more effective when you're farther from the axis of rotation that it's pivoted about. Similarly, you know, if I'm trying to open the door, well, if I pull along the direction from the point I'm going to apply the force here, if I pull along the direction from where I'm applying the force toward the axis, it doesn't help at all that I'm pulling in this direction, does it, to open the door? Now it gets a little bit more effective if I pull outward a little bit, then I can pull a little bit, but everybody kind of intuitively knows if you're going to open the door, you pull in the direction perpendicular to the point where you're grabbing it. So it's in the same way, it's completely ineffective for me to pull toward the axis or directly away from the axis. It gets more effective as it becomes more perpendicular, okay? So this idea of trying to get things to start rotating or get unstuck, but a lot of times it'll just be some heavy object that's really hard to get rotating. That is kind of the idea of a torque. A force is something that we use to get an object moving linearly. A torque is the angular analogy to force that we use to try to get things rotating rather than moving linearly. Okay, so E is the best answer there. And most of us, you know, you give someone a door and you don't tell them to think about it, they'll naturally grab it far from the axis and pull perpendicular. Try it yourself sometime when you're not thinking about it, because if you overthink it, of course, it makes it more difficult. Okay, so torque is, in words, this isn't precise here. We'll define it with an equation just in a second, but it's a measure of the effectiveness of an applied force at starting rotation about a certain axis. The same force can be either very effective or very ineffective. So we want to be able to calculate something with that force that tells us how good it's going to be at rotating. Okay, so let's define torque here. Let's imagine I've just got an arbitrary object maybe, and it's got a fixed rotation axis. I'm thinking of this rotation axis as coming out of the screen here. And I'm applying a force up at some random position in a random direction. And most of it, you know, hopefully you have the intuition that if you pull there, at least for the initial motion, it's going to start moving a little bit counterclockwise, right? If I attach a string or a cable to there and I start pulling, it's going to cause it to move at least a little bit in that direction. Then the angle of the string would change and it might get a little bit confusing after that. But at least initially, it's going to cause it to rotate, the top to rotate to the left. Let's define what the torque is. So, and then we'll try to make sure that it matches up with our intuition. Let's say, okay, our force is defined as the vector F. Let's say we're applying that force at a certain location on the object. By definition, this vector R is going to be a vector that points from the axis of rotation to the point at which we're applying the force. Okay, that's what we're going to call R. And I'm going to construct some different ways of calculating the torque. We'll actually do it 3 different ways. Let's continue the line along R past the point at which the force is being applied. And what I'm going to do is take the component of the force that's perpendicular to that line that includes R, right? So I go along R, take the component of the force that's perpendicular to it. I'm going to call that F perpendicular. It's the perpendicular component of the force that's important for torque, right? If I pull twice as hard along this direction, it's not going to cause it to rotate at all, right? I'll just be pulling on the hinge, but it won't cause it to rotate around the hinge at all. What matters is how big this perpendicular force component is. Okay, so, oops. The torque is going to be defined as the length of this R vector, how far the force is that's applied from the point at which it's applied to the axis of rotation, times the perpendicular component of the force. And perpendicular means perpendicular to the r direction in this case, okay? So notice that just like we talked about with the door, the bigger F perpendicular is, the bigger the torque. We want to make F perpendicular big to be successful at turning it. But also, the further away I apply the force, the bigger the torque. So that agrees with those things that hopefully at least are semi-intuitive about applying torques. There's a sign convention for torque. You know, conventionally, we have to say which way is the positive rotation direction. And that's because, you know, if I'm sitting here looking at this screen and I say, oh, I've got an unambiguous convention that counterclockwise rotations are positive. That's what I'm saying right here. Someone might be looking at the same object, but from behind the screen. And when they look at it, they would say, well, wait a minute, your positive direction is now clockwise, not counterclockwise. And so you need to draw it in the diagram. And I'm going to say, you know, I'm not going to say clockwise or counterclockwise. I'm just going to draw a direction of rotation around the axis and say, that's my positive direction. We can't rely on clockwise and counterclockwise because when you look from the other side, they switch between the two. So whenever I'm calculating torques and also using the kinematic stuff, it helps to just draw which is the positive rotation direction. Okay, the convention for the sign of torque is we're going to say a positive torque is one that tries to increase theta. So this is the direction of increasing theta, the positive rotation direction. So I would say that this force is going to try to rotate it in the positive direction, at least at the instant that's shown right there, right? It's going to cause it to rotate that way. Whereas a negative torque by this sign convention is going to be one that would try to rotate it in this direction, the negative direction, however you defined it. And it's okay to draw the positive direction the opposite, like I can make it clockwise as well. Okay, that's the first formula associated with torque. Here's a second formula. Well, look, you know, if I define this angle theta in between the F vector and the direction the R vector was headed, define that angle to be theta, then if I do the magnitude of F times the sine of theta, that's going to give me this component of F, which is the same as this component of F, right? Those are the same distances. And so F perpendicular is really nothing but F sine theta. So another way you'll see it written in the book is RF sine theta. Here, I'm not doing F perpendicular. This is the full magnitude of R times the full magnitude of the force times the sine of the angle between them. And that means if you continue that R vector forward, what's the angle between F and R? Okay. Third way we're going to define it, third and final way, and we'll find that all three of these are useful in different kinds of problems depending on what's given, is we're going to take the F direction and draw the line that contains the vector F. Wherever it's being applied, draw a line that contains it. You can draw it forward or backward, depending on what you need. And what we're going to do is construct the component of R that is perpendicular to that direction that we've just, you know, the line that contains F, right? So if I said, here's a vector R, but its component which is perpendicular to the dashed black line is this one. We're going to call that R perpendicular, which by, you know, most people call that the moment arm for the force that's delivering the torque. So how big your moment arm is this. You look at where your force is being applied, you go directly backwards along that force direction, and you're interested in how far is the perpendicular direction from the distance from there to the axis of rotation. Okay, so three different ways of calculating the torque. They're all the same. You can see that they're the same here in that, look, we already showed the first two are the same, but if I put the sine theta next to the R, if this angle is theta, this angle here is also theta. And if I do magnitude of R times the sine of theta, isn't that nothing but R perpendicular? So this is just a double rebranding of the same formula over and over again, but it kind of feels a little bit different. Sometimes you'll be able to look at a problem and you'll say, oh, they're giving me the moment arm. So use that formula. Sometimes you'll obviously see what the perpendicular component of the force is. Okay, use that form of the formula. And sometimes you'll be given this angle, and then you might want to use the one with the sine of theta. So do whatever's easiest. Let's just look at an example, and this is probably all we have time for in the last couple of minutes. So here I'm just, because I can draw pentagons easily in PowerPoint, my object is a pentagon. I'm imagining its fixed axis of rotation is down here. And we're given some exact information about exactly where I'm applying the force. I'm applying the force at a point that is 0.2 meters away from the axis of rotation along a line 20 degrees above the horizontal in my diagram, okay? And the force I'm applying is exactly vertical in the diagram, okay? So it's going straight up and down the page, magnitude 5 newtons. Let's calculate the torque, and we'll do it all 3 ways here to show that you really can do it using any one of these. Let's first do it with the first formula. R times the perpendicular component of F. So in this case, I don't have to do anything with R. R is just how far from where you're applying the force to the axis. That's 0.2 meters. To get the perpendicular component of the force, I need to draw a little right triangle here. Here is the perpendicular component of the force. It's going to be 5 times the sine of 70 degrees. Okay, so there it is. Notice that for the second case, I don't really have to do anything different. I already had this angle marked here. That's the angle we're talking about as was defined as theta for the second version of the formula. It is, if you keep going forward with respect to R, how far do you have to rotate around to get to the F? So full R times full F times the sine of that angle. Of course, it's the same exact formula that we got before. Let's calculate with the moment arm now. If I figure out what the moment arm is, what that means is I have to project this force vector or draw the line that contains the force vector back and find that perpendicular distance. So if I do that, I would have to draw a little right, complete the right triangle there, and I'm looking for this distance. That's going to be 0.2 times the cosine of 20. Fortunately, the cosine of 20 is exactly the same thing as the sine of 70, so it gives exactly the same number no matter which way you do it. And so whichever one you see first, you just go with it. You don't have to worry about which one is the right formula. They're all right for the right problem. If I wanted to put in a sign for the torque, I didn't before specify which way was the positive direction, but let's take positive to be clockwise in this case. Well, what do you guys say about the sign of the torque here? Positive or negative? It's negative. We say, which way is this applied force going to try to twist it? And everybody seems to have the intuition that's going to try to twist it around in the counterclockwise direction, which is negative by my axis choice. So if I'm choosing that axis, my torque should actually have a minus sign in all 3 of those cases. All right, it's 4 o'clock, so let's call it quits there. And I think before Friday, you're supposed to read the remaining sections of chapter 8. We've got quite a bit of distance to go, so it'll probably be Monday before we finish, I would imagine. And next week, we'll be doing an experiment in lab having to do with torque. So